So when we're valuing a zero coupon bond, we take an expectation over the pricing. And how do we do that? We'll get now into some detail. Well, here's our risk-neutral process. We're going to generate R using, again, we need presumably we have an A function, a sigma function, and we need a phi function. We need that. But once we have that, how do we calculate this expected value? What does that mean? Well, the point is we can approximate an integral with a Riemann sum. This should look familiar. That if I break the interval t to capital T up into n steps, the usual procedure, I can approximate the integral by a Riemann sum, which is nothing more than a product of delta S is my notation for capital T minus little t over n. It's delta S is t minus t over n, so it's n is the number of steps, and I approximate. So what remains for any n is how do I generate those R values? And let's look at that next. Well, we have a process, and the process says dr is equal to, and I'm going to simplify the notation here, and let's use the notation capital A of R t dt plus sigma of R dz. And what I'm going to do is simplify the notation that my capital A of RT is that expression from the earlier, namely it's a little a of R minus sigma R times phi of RT. Okay, so just for our notational convenience, capital A is a function of R and T, and I'm just using it to simplify my notation so I don't have to write so much here. So what we know is we have an R of T at time 0. R of 0 is just the initial overnight rate. So we know R is 0. Now how do we then generate successive values of R according to this? Well, this stochastic equation says that R1 is equal to R0 plus dr. And dr is the change in R associated with whatever time interval we're modeling. So we've picked a time interval. And once we do that, what we're going to do is say this is equal to R0 plus, what's the approximation for dr? Well, this formula says take the A function and evaluate it at R0 times 0 and multiply that times delta t, whatever my time interval is. Take the function sigma, evaluate it at R0, and let's remember what dz is. dz can be thought of as square root of delta t times a normal z. Namely, at the end of one period, Brownian motion has a mean of 0 and a variance of delta t. So it's easier for me to write this as square root of delta t times a standard normal. So z1 is a standard normal. All of my z's are going to be standard normals. So now I have R1. That's the estimate based on this process of the value of the overnight rate at time delta t. Now we're going to take another step. What's R2? R2, this is R of delta t, is R1. Now I'm going to do R of 2 delta t. That's R2. Same process. R2 is R1 plus a new dr. What is the new dr? Well, this process says that you always have to evaluate A at the beginning of the interval. So now it's evaluated at R1 delta t. We're evaluating A at the point R1 that occurs at time delta t. Multiply that by delta t. Do the same. We now have sigma evaluated at R1, square root of delta t, and we have a new z. And we continue in this until we finally get R at time in the summation, we only needed up to n minus 1 delta t. And that by definition is r n minus 2, the last one we calculated, plus a new dr. And the only thing is that each of the coefficients of our stochastic process needs to be evaluated at the prior point in time. So on a timeline, we have 0, and to get the value at time 1, delta t that is, that we're saying R1 is a function of R0 and 0. And we have to use R0 and time 0 in all of our functions. When we get to 2 delta t, R2 is a function of the value R1 and the time delta t. So think of it as every time we're generating, and this is the same with generating successive stock values stochastically, we use information at the beginning of the period that we're projecting. And in each step, we need a random variable. So notice that after we get done producing a sequence of these R values, that's one path of interest rates. And we have to do this, say, 1,000 times. And then we go back to our formula. Because we can approximate the integral with this Riemann sum, when I do an expectation, the expected value now, with the risk-neutral process of e to the minus r, what that means is it's nothing more than an average. Let's say that I did 1,000 of these paths. I would simply do 1 over 1,000 times a summation of e of all the prices I get. I'm going to generate 1,000 values of capital R, each one of those being an integral, and each one of those rj's comes from one of my paths. It's equal to t minus t over n times a summation from Ri from 0 to n minus 1. Basically I'm approximating the integral of the R of S ds. So and I'll put a j up here just to denote that every one of my capital R's has a subscript j because it represents the jth process that I generated. So if I have 100 steps in my time interval, I have to generate 100 normal variables. That gives me one path of interest rates, and then I repeat that process 1,000 times, get 1,000 values of capital R, and then I average those 0 prices. And that's what the Cox-Ingersoll-Ross result is. It's that the price of that 0 coupon bond is the average of prices you get by generating interest rates using the risk-neutral process. So it's actually a mouthful. It's a lot to communicate, but in practice, it is not difficult to generate these R's randomly and to calculate these expectations. The difficulties, of course, are related to the parameters of the process determining what they are. And if we determine those parameters differently, we will get different prices of these bonds. So what people often do is, when they're working with these models, is they determine the parameters in such a way that they can best price as many bonds as possible and are in the market. More on that coming up.